Hello everyone. So in this video, I'm going to talk about some features about BCNF and then sort of set the stage for the 3NF algorithm. Okay. So when we are evaluating BCNF, or for that matter, when you are evaluating any decomposition algorithm, right? There are two aspects which are very important. Of course, the aspect zero, so to say, is that we should have minimum data redundancy, and the you should not have update and delete anomalies. So that is sort of step zero, if you will. And beyond that, there are two other things which are of importance. So so one is the characteristic of what we call as lossless decomposition, and the second one being functional dependency preservation, right? So in lossless decomposition, what we require is that if we were to join back the decomposed relations, we should get back the original relation, and there should be no new tuples. That means data should neither be destroyed nor a new data should be created, right? So even if you go back a couple of slides, when we decomposed our sample R into these three, right? Then when we the requirement of lossless decomposition is that when we join these three relations back, we should get our sample R, the original relation, right? So this is what is meant by lossless decomposition, right? And this is also this is so important. The property of lossless decomposition is that any normalization algorithm which does not follow lossless decomposition is just considered garbage. It's not even studied anywhere. It the textbooks don't even consider it, right? So you can just sort of take it for now that BCNF and 3NF, whichever we are going to study, uh, they will have lossless decomposition, right? Otherwise it's not even worth studying, right? And what is lossless decomposition? If we are given a big table and we decompose it and we try to join back the decomposed relations, we should get back the original relation. And in this process, no tuple should be lost, and no new tuple which was previously not present, it should not be created, right? So data should neither be lost or new one be created which is not originally there. So that is lossless decomposition. We'll cover more of this in an different video if time permits. There is something called as chase test. We'll see if we can cover that. And second one being the functional dependency preservation. So in functional dependency preservation, the requirement is that all the FDs which hold on the original relation should somehow translate onto some equivalent FDs on the decomposed relation, right? So if there were some a bunch of constraints which were there in your original R, and then you decompose that R into a bunch of children relations, then all the FDs which were held on the original one should somehow try to translate, right? So this is an important part because the BCNF algorithm which we studied does not have this functional dependency preservation, right? And we'll just see an example of how that can happen. Uh, Nevertheless, BCNF is still very, very widely used. Uh, the next normalization algorithm, which is 3NF, will guarantee both of these. But the downside of 3NF is that there is little bit of extra redundancy, right? Even in the example that I'm going to cover for loss of functional dependency preservation, you'll see that that is a highly contrived example, and much more related to a theory angle rather than having a lot of significance in real world, right? So by the moral of the story here is that don't throw away BCNF as an useless decomposition. It is still extremely widely used. right? Because only there are only just very few functional dependencies which do not translate down. Rest everything gets covered. Okay. Okay. So let's see what kind of FDs do not translate downwards in BCNF, right? Okay. So the example being that, let's say that, you have a relation ABC and you have these two FDs, AB implies C and then C implies B, right? So if you want a real life example, the textbook author took the case of US street addresses, right? So the address in United States, the way it works is that you have a street address. So that means, plot number followed by some street number and then city and zip code, right? And it may happen that, two different addresses, let's say you pick an address like plot number 100, 7th street, right? So different cities may have the same plot number and street number, but in a particular city, that is sort of taken care of. Okay. So we'll see when we go there. But for now, you can even imagine the FDs like this. AB implies C and then C implies B, right? So these are the two FDs, and your relation has only three attributes. So in a case like this, you have two keys. So either AB will become a key because closure of this will have all the attributes, or AC can also be a key, right? Because closure of this will also contain all the attributes, right? So now what happens is that if you go with the BCNF definition, this particular FD, C implies B, this causes a BCNF violation, right? So therefore, we decompose the relation and, just two attributes, with just one FD you're decomposing, you end up with a case like this, AC and BC, right? Now what happens is that in the decomposed relation, these two relations AC and BC, you cannot enforce the FD AB implies C. That is the problem, right? And as per your textbooks, this is just about one very rare cases, So that's why I said that, the example which I'm going to show you for loss of functional dependency preservation, it will look like very contrived. So it is much more from a theory angle, but nevertheless, we should understand the fact that BCNF cannot guarantee 100% functional dependency preservation. Okay, so let's see an example of that. So let's say, this is our table: street, city, and zip code. So our street addresses are like this, 204th Street, 205th Street, and so on. And then you have the city information, and then you have the zip code. Let's say, this is your original table storing the addresses, and then you have the functional dependencies wherein the two functional dependencies which are coming from your business logic is that, given a street and a city, you can uniquely identify the zip code, right? So that means the combination of street and city can uniquely identify, tell you the zip code. Okay, and then you have that, the second FD being that, zip code also can uniquely tell you the city, right? So given any zip code with that will, belong to only one particular city, right? So in a relation like this, you have two keys. So one is, of course, the combination of city and street address, right? And then the other combination would be street address and zip code. They both will be the keys of this particular relation. Now, as I said before, this causes trouble. Zip code implies city. This FD causes trouble. So you perform the decomposition of this table, right? So when you perform the decomposition, you'll get two tables, city and zip, and then street address and the zip code, right? So now what happened, all the original addresses which you had in the original table, they will nicely sort of, filter out into these two child tables. Uh, So that part is fine, but what happens is that the functional dependencies which we're holding in the original table, they don't translate to the children table. So for example, zip implies city, right? That can be enforced on this particular table. Okay, so how will you do that? You can just make zip as the primary key, and this FD is now enforced. That's how you try to enforce an FD, right? Whereas this particular FD, street city zip, that kind of FD does not translate anywhere, because there is no table which has all the three tables in all the three attributes, right? So, and that gets to problem, right? Suddenly, in your business logic, uh, you had two FDs, but when you created the schema, when you have this schema, one FD is now completely missing from this schema, right? So there is no way you can enforce the FD which says street and city implies zip code, right? So this FD cannot be enforced at this decomposed level. Okay. Now how does that create trouble? Okay. Now let's click forward. Okay. So given that no FD is coming here, right? I can insert a tuple like this: 200 4th Street with this zip code. Okay, I can do it because there is no FD here. I can do that. So once a tuple like this comes in, what happens is that if you were to join this, suddenly you are getting this spurious tuple, which is not a valid thing, right? So now what has happened is that this was more of an example, right? Remember that when we decomposed our original table into two child tables, right? The original table is no longer stored, right? And the all we are now working is with these decomposed tables, right? Now what is happening is that in these decomposed tables, we are not able to enforce all our FDs, and as a result of that, what is happening is that at the full database level, one FD is missing now, right? So this particular FD, street and city implies zip code. This particular FD, gets violated when you see the whole data which is stored at the decomposed level. That is the problem. Okay, so your textbook also gives another example, but essentially it's the same class of functional dependencies. Same style of functional dependencies. You have two FDs, ABC. AB implies C, and then C implies B. Right. So this is a BCNF violation. You do the decomposition, and suddenly you realize that this FD cannot be enforced, right? And if an FD cannot be enforced at the decomposed level, then what is happening is that you are enabling some troubled data to get into your database system, which does not uh, follow your business logic constraints. That is the whole story of why FDs cannot be enforced, right? So so go through this carefully, and if you have any doubts, let me know. Textbook also has another example, but essentially it's the same style of doing things. Okay, so that was the problem of BCNF. So there is another normalization technique. This is called as the third normal form. We'll cover this in the next video. What it does is that it addresses this small problem of BCNF, right? Uh, so before I give you a formal definition, there is something called as a prime attribute, right? So an attribute is called as a prime attribute if it is a member of any key of the relation, right? Again, an attribute is called as a prime attribute if it is a part, or if it shows up as a part in any key of your given relation R, right? So now with this definition, 3NF is defined as follows, right? Uh, any given FD, X implies A. We say that X implies A violates 3NF if and only if X is not a super key and A is not an prime attribute. Okay. So now let us go back to our example here. So in this case, when we had that ABC relation, and then with these two FDs, AB implies C and C implies B, we had two keys, AB and AC, right? So now what happens is that, each of these are prime attributes. So because A is a part of two keys, B is a part of this key, and C is a part of this key, right? So essentially all the three attributes are prime attributes in case. But that's not really the big deal. The big deal is that this functional dependency C implies B, which created trouble for your BCNF, does not create trouble for your 3NF algorithm. So 3NF says that either the left side should be a super key. Unfortunately, it is not in this case, or the right side should be part of some key. So B is part of at least one key. In other words, B is an prime attribute. So whenever you have FDs like this, the 3NF algorithm lets it go, right? It does not cause trouble, and it does not go for decomposition, whereas BCNF got hung up on this. That is the only difference between BCNF and 3NF. Otherwise, this part that X has to be a super key, that part remains the same. It's just the another way to think of is that 3NF can be probably considered as slightly looser version, right? Now what happens when I put when I relax this kind of a thing, right? So when you relax this kind of a thing, what happens is that this table, with all these both these FDs, this was not in BCNF because of this particular FD, right? But now I'll say that these two, both these FDs are allowed, because over here city is an prime attribute, it is part of a key, right? So this table will no longer be decomposed in 3NF. So what happens is that there is bit of a redundancy that is going on here, and that redundancy is in the column of the city, right? So consider this. So let's say that you pick a zip code, whatever zip code it is, and then there are several street addresses which are coming in a zip code, right? Because zip code is a postal code sort of a thing. Several street addresses come into that particular zip code. Now, given that you have put the city column also in this very table and you are not letting it to decompose, what is happening is that you are repeating the city information across all the street addresses which are belonging to one particular zip code, right? So this is the FD which is creating that, right? So you have to keep repeating the city name, whatever it is, Ropar or Cambridge, for all the addresses which belong to one particular zip code, right? So that is the pros and cons of 3NF. So 3NF allows functional dependency conservation, and it can be theoretically proved also, but it has some kind of a redundancy. BCNF goes very hard on redundancy removal, but in doing so it may lose some FD preservation. Okay. Yeah, so this is sort of the summary slide. Okay. Now, two properties, lossless decomposition, dependency preservation, and probably a step 0, which is saying that removal of redundancy, right? So now BCNF will give you lossless decomposition. That means it will give you recovery, and it will also minimize the data redundancy part, right? But in 3NF, what happens is that you cannot have zero redundancy, But the pro side is that you have lossless decomposition and functional dependency preservation. So that is sort of the pros and cons of BCNF and 3NF. Okay.